How's it going? After the round one quick reading, I still I still think that I'm not ready to do the exercise in this book. So I decided to do a a deep reading one more time. This time uh, I'm going to read this book slowly and figure out where I miss the words that I don't understand, and I will note it, and I will figure it out. So here we go. Uh, from preface, as usual, C is a general purpose programming language which features economy of expression, modern control flow, and data structures. In a rich set of operators, C is not a very high-level language, nor a big one, and is not specialized to any particular area of application. But its absence of restrictions and its generality and its generality but its absence of restrictions and its generality make it more convenient and effective for many tasks than supposedly more powerful languages. C was originally designed for the implemented on the Unix operating system and the DCPDP-11 by Dennis Ratio. The operating system, the C compiler, and essentially all Unix applications, programs, including all of the software used to prepare this book, are written in C. Production compilers also exist for several other machines, including the IBM system /370, the Honeywell 6000, and the Interdata 8/32. C is not tied to any particular hardware or system, however, and it is easy to write programs that will run without change on any machine that supports C. This book is meant to help the reader learn how to program in C. It contains a tutorial introduction to get new users started as soon as possible, separate chapters on each major feature, and a reference manual. Most of the treatment is based on reading, writing, and revising examples, rather than on mere statements of rules. For the most part, the examples are complete, real programs rather than isolated fragments. All examples have been tested directly from the text, which is in machine-readable form. Besides showing how to make effective use of the language, we have also tried, where possible, to illustrate useful algorithms and principles of good style and sound design. This book is not an introductory programming manual. It assumes some familiarity with basic programming concepts like variables, assignment statements, loops, and functions. Nonetheless, a novice programmer should be able to read along and pick up the language, although access to a more knowledgeable colleague will help. In our experience, C has proven to be a pleasant, expressive, and versatile language for a wide variety of programs. It is easy to learn, and it wears well as one's experience with it grows. We hope that this book will help you to use it well. The thoughtful criticisms and suggestions of many friends and colleagues have added greatly to this book and to our pleasure in writing it. In particular, Mike Benchy, Jim Blue, Stu Fieldman, Doug McCoy, Bill Roman, Bob Rosin, and Larry Rossler all read multiple versions with care. We are also indebted to Al Hall, Stephen Barney, Dan DeFrog, Chuck Haley, Debbie Haley, Marianne Harris, Rick Hollett, Steve Johnson, John Marshy, Bob Meads, Rafa Muha, Peter Nielsen, Elliot Pinson, Bill Plugger, Jerry Spivak, King Thompson, and Peter Weinberg for helpful comments at various stages, and to Mike Lesk and Joe Asana for invaluable assistance with typing set. From Brian W. Cunningham, Dennis M. Rachel. Chapter 0, Introduction. C is a general-purpose programming language. It has been closely associated with the Unix system since it was developed on that system, and since Unix and its software are written in C. The language, however, is not tied to any one operating system or machine, and although it has been called a system programming language because it is useful for writing operating systems, it has been used equally well to write major numeric, text processing, and database programs. C is a relatively low-level language. This characterization is not pejorative. It simply means that C deals with the same sort of objects that most computers do, namely characters, numbers, and addresses. This may be combined and moved about with the usual arithmetic and logic operators implemented by actual machines. C provides no operations to deal directly with composite objects such as character strings, sets, lists, or arrays considered as a whole. There is no analog, for example, of the PL/I operations, which manipulate an entire array or string The language does not define any storage allocation facility other than static definition, and stack discoupling provided by the local variables of functions. There is no heap or garbage collection like that provided by Article 68. Finally, C itself provides no input-output facilities. There are no read or write statements and no wired-in file access methods. All of these higher-level mechanisms must be provided by explicitly called functions. Similarly, C offers only straightforward single-thread control flow constructions, tests, loops, grouping, and subprograms, but not multi-programming parallel operations. Synchronization, or coroutines. Although the absence of some of these features may seem like a grave deficiency, you mean I have to call a function to compare two character strings, keeping the language down to modest dimensions, has brought real benefits. Hang on. Since C is relatively small, it can be described in a small space. And learned quickly. A compiler for C can be simple and compact. Compilers are also easily written. Using current technology, one can expect to prepare a compiler for a new machine in a couple of months and to find that 80% of the code of a new compiler is common with existing ones. This provides a high degree of language mobility because the data types and control structures provided by C are supported directly by most existing computers. The runtime library required to implement self-contained programs is tiny. On the PDP-11, for example, it contains only the routines to do 32-bit multiplication and division and to perform the subroutine entry and exact sequences. Of course, each implementation provides a comprehensive, compatible library of functions to carry out I/O, string handling, and storage allocation operations. But since they are called only explicitly, they can be avoided if required. They can also be written portably in C itself. Again, because the language reflects the capabilities of current computers, C programs tend to be efficient enough that there is no compulsion to write assembly language instead. The most obvious example of this is the Unix system itself, which is written almost entirely in C. Of 13,000 lines of system code, only about 800 lines at the very lowest level are in assembler. In addition, essentially all of Unix applications software is written in C. The vast majority of Unix users, including one of the authors of this book, do not even know the PDP-11 assembly language. Although C matches the capabilities of many computers, it is independent of any particular machine architecture, and so, with a little care, it is easy to write portable programs, that is, programs which can be run without change on a variety of hardware. It is now routine in our environment that software developed on Unix is transported to the local Honeywell, IBM, and Integrated Systems. In fact, the C compilers and runtime support on these four machines are much more compatible than the supposedly NC standard versions of Fortran. The Unix operating system itself now runs on both the PDP-11 and the Interdata 8/32. Outside of programs which are necessarily somewhat machine-dependent, like the compiler assembler and debugger, the software written in C is identical on both machines within the operating system itself. The 7,000 lines of code outside of the assembly language support and the ICE natural device handlers is about 95% identical. For programmers familiar with other languages, it may prove helpful to mention a few historical, technical, and philosophical aspects of C for contrast and comparison. Many of the most important ideas of C stem from the considerably older, but still quite fiddle language BCPL, developed by Martin Richards, and the influence of BCPL on C proceeded indirectly through the language B, which was written by Ken Sampson in 1970 for the first Unix system on the PDP-7. Although it shares several characteristic features with BCPL, C is in nonsense a dialect of it. BCPL and B are typeless languages. The only data type is the machine word, and access to other kinds of objects is by special operators or function calls. In C, the fundamental data objects are characters, integers of several sizes, and floating point numbers. In addition, there is a hierarchy of derived data types created with pointers, arrays, structures, unions, and functions. C provides the fundamental flow control constructions required for well-structured programs: statement grouping, decision-making, looping with the termination test at the top or at the bottom, and selecting one of a set of possible cases. All of these are provided in BCPL as well, though with somewhat different syntax. That language anticipated the vogue for structured programming by several years. C provides pointers and the ability to do address arithmetic. The arguments to functions are passed by copying the value of the argument, and it is impossible for the called function to change the actual argument in the caller. When it is desired to achieve call by reference, a pointer may be passed explicitly. And the function may change the object to which the pointer points. Array names are passed into the location of the array origin. So array arguments are effectively called by reference. Any function may be called recursively, and its local variables are typically automatic or created anew with each invocation. Function definitions may not be nested by variables, may be declared in a block structured fashion. The functions of a C program may be compiled separately. Variables may be internal to a function, external but known only within a single source file, or completely global. Internal variables may be automatic or static. Automatic variables may be placed in registers for increased efficiency. But the register declaration is only a hint to the compiler and does not refer to specific machine registers. C is not a strongly typed language in the sense of Pascal or Argo 68. It is relatively permissive about data conversion, although it will not automatically convert data types with the wild abandon of PL/I. Existing compilers provide no runtime checking of array subscripts, argument types, etc. For those situations where strong type checking is desirable, a separate version of the compiler is used. This program is called lint, apparently because it picks bits of fluff from one's programs. Lint does not generate code, but instead applies a very strict check to as many aspects of a program as can be verified at compile and load time. It detects type mismatches, inconsistent argument usage, unused or apparently uninitialized variables, potential portability difficulties, and the like. Programs will pass unscathed through lint enjoy, with few exceptions, freedom from type errors about as complete as do, for example, Argo 68 programs. We will mention other linked capabilities as the occasion arises. Finally, C, like any other language, has its blemishes. Some of the operators have the wrong precedence. Some part of the syntax could be better. There are several versions of the language extant, differing in minor ways. Nonetheless, C has proven to be an extremely effective and expressive language for a wide variety of programming applications. The rest of the book is organized as follows. Chapter 1 is a tutorial introduction to the central part of the HANA. The purpose is to get the reader. Okay, I'm sorry, hang on. I got something loose. The purpose is to get the reader started as quickly as possible, since we believe strongly that the only way to learn a new language is to write programs in it. The tutorial does assume a working knowledge of the basic elements of programming. There is no explanation of computers, of compilation, nor of the meaning of an expression like n equal n plus 1. Although we have tried where possible to show useful programming techniques, the book is not intended to be a reference work on data structures and algorithms. When forced to a choice, we have concentrated on the language. Chapters 2 through 6 discuss various aspects of C in more detail, and rather more formally than does Chapter 1. Although the emphasis is still on examples of complete, useful programs rather than isolated fragments, Chapter 2 deals with the basic data types, operators, and expressions. Chapter 3 treats control flow, if else, while, for, etc. Chapter 4 covers functions and program structure, external variables, scope rules, and so on. Chapter 5 discusses pointers and address arithmetic. Chapter 6 contains the details of structures and unions. Chapter 7 describes the standard C international library, which provides a common interface to the operating system. This international library is supported on all machines that support C, subprograms which use it for input-output, and other system functions can be moved from one system to another essentially without change. Chapter 8 describes the interface between C programs and the Unix operating system, concentrating on input/output, the file system, and portability. Although some of this chapter is Unix specific, programmers who are not using an Unix system should still find useful material here, including some insight into how one version of the standard library is implemented, and suggestions on achieving portable code. Appendix A contains the C reference manual. This is the official statement of the syntax and semantics of C, and except for one's own compiler, the final arbiter of any ambiguities and omissions from the earlier chapters. Since C is an evolving language that exists on a variety of systems, some of the material in this book may not correspond to the current state of development for a particular system we have tried to steer clear of such problems and to warn of potential difficulties when in doubt. However, we have generally chosen to describe the PDP-11 Unix situation, since that is the environment of the majority of C programmers. Appendix A also describes implementation differences on the major C systems. You know, Chapter 1, a tutorial introduction. What is the difference with the Chapter 0? Let us begin with a quick introduction to C. Our aim is to show the essential elements of the language in real programs, but without getting bogged down in details. Formal rules and exceptions at this point, we're not trying to be complete or even precise, such that the examples are meant to be correct. We want to get you as quickly as possible to the point where you can write useful programs. And to do that, we have to concentrate on the basics, variables and constants, arithmetic control flow functions, and the root and the and the rudiment and the rudiment and the rudiments and the rudiments of input and output. We're quite intentionally leaving out of this chapter features of C which are of vital importance for writing bigger programs. These include pointers, structures, most of these rich set of operators, several control flow statements, and myriad details. This approach has its drawbacks. Yeah, yeah. Of course, most notable is that the complete story of any particular language feature is not found in a single place, and the tutorial, by being brief, may also mislead, and because they cannot use the full power of C, the examples are not as concise as concise. The examples are not as concise and elegant as they might be. We have tried to minimize these effects, but be warned, you know, another drawback is that later chapters will necessarily repeat some of this chapter. We hope that the repetition will help you more than it annoys. In any case, experienced programmers should be able to extrapolate from the material in this chapter to their own programming needs. Beginners should supplement it by writing small, similar programs of their own. Both groups can use it as a framework on which to hang the more detailed descriptions that begin in Chapter 2. 1.1 Getting Started. The only way to learn a new programming language is by writing programs in it. The first program to write is the same for all languages. Print the words "Hello World." This is the basic hurdle. To leap over it, you have to be able to create the program. Text somewhere, compile it successfully, load it, run it, and find out where your output went. With this mechanical details mastered, everything else is comparatively easy. In C, the program to print "Hello World" is like this. Just how main parentheses, braces, printf, parentheses, double quote, hello world, hello comma word, backslash, and semicolon. Just how to run this program depends on the system you are using. As a specific example, on the Unix operating system, you must create the source program in a file whose name ends in .c, such as hello.c, hello.c. Then compile it with the command cc hello.c. If you haven't botched anything, such as omitting a character or misspelling something, the compilation will proceed silently and make an executable file called a.out. Running that by the command a.out will produce hello, world. As its output on other systems, the rules will be different. Check with a local expert. Exercise 1, middle score 1. Run this program on your system. Experiment with leaving out parts of the program to see what error messages you get. Now, for some explanations about the program itself, a C program, whatever its size, consists of one or more functions which specify the actual computing operators that are to be done. C functions are similar to the functions and subroutines of a Fortran program or the procedures of pl/hang. In our example, main is such a function. Normally, you're at liberty to give functions whatever names you like. But main is a special name. Your program begins executing at the beginning of main. This means that every program must have a main somewhere. Main will usually invoke other functions to perform its job. Some coming from the same program, and others from libraries of previously written functions. One method of communicating data between functions is by arguments. The parentheses following the function name surround the argument list. Here main is a function of no arguments, indicated by parentheses. The braces enclose the statements that make up the function. There are analogous to the do end of PL/I or the begin end of Argo, Pascal, and so on. A function is invoked by naming it, followed by a parenthesized list of arguments. There is no call statement as there is in Fortran or PL/I. The parentheses must be present even there are no arguments. The line that says printf parentheses hello world \n semicolon. I lost double quotes. Is a function call which calls a function named printf with the argument hello world \n. Printf is a library function which prints output on the terminal. Parentheses unless some other destination is specified. In this case, it prints the string of characters that make up its argument. A subsequence of any number of characters enclosed in the double quotes is called a character string or string constant. For the moment, our only use of character strings will be as arguments for printf and other functions. The subsequence \n in the string is C notation for the new line character, which when printed advances the terminal to the left margin on the next line. If you leave out the \n, a worthwhile experiment, you will find that your output is not terminated by a line feed. The only way to get a new line character into the printf argument is with \n. If you're trying something like printf parentheses double quotes hello world semicolon, the C compiler will print a friendly diagnostics about missing quotes. Printf never supplies a new line automatically, so multiple calls may be used to build up an output line in stages. Our first program could just as well have been written. Main parentheses braces printf parentheses double quotes hello semicolon word semicolon \m to produce an identical output. Notice that \n represents only a single character. An escape sequence like \n provides a general and extensible mechanism for representing hard to get or invisible characters. Among the others that C provides are \t for tab, \p for backspace, quote double quote for the double quote, and for itself. Hang on, I got something to record. Like this. Okay. Exercise 1-2. Experiment to find out what happens when printf's argument string contains \x, where x is some character not listed above. 1.2 Variables and arithmetic. The next program prints the following table of Fahrenheit temperatures and their centigrade or Celsius equivalents. Using the formula C equal parenthesis 5/9 parenthesis F minus 32. C is uppercase C, F is uppercase F, like this table. Here is the program itself. Okay, this exercise I have already do it right and correct many times, and I figured it out, and I knew it exactly. So far, it's known. The first two lines are a command, which in this case explains briefly what the program does. Any characters between /* and */ are ignored by the compiler. They may be used freely to make a program easier to understand. Comments may appear anywhere a blank or new line can. In C, all variables must be declared before use, usually at the beginning of the function before any executable statements. If you forget a declaration, you will get a diagnostic from the compiler. A declaration consists of a type and a list of variables which have that type is in int lower upper step float Fahrenheit Celsius. The type int implies that the variables listed are integers. Float stands for floating point. I.E. numbers, which may have a fractional part. The precision of both int and float depends on the particular machine you are using. On the PDP-11, for instance, an int is a 16-bit signed number, that is 1, which lies between minus 62768 and plus 62767. A float number is a 32-bit quantity, which amounts to about 7 significant digits, with magnitude between about 10 powers minus 38 and 10 powers plus 38. Chapter 2 lists sizes for other machines. C provides several other basic data types besides int and float. The sizes of these objects are also machine dependent. Details are in Chapter 2. There are also arrays, structures, and unions of these basic types, pointers to them, and functions that return them, all of which we will meet in due course. Actual computation and the temperature conversion program begins with the assignments. Lower equals 0, upper equals 300, step equal 20, Farad equal lower, which set the variables to their starting values. Individual statements are terminated by semicolons. Each line of the table is computed the same way, so we use a loop which repeats once per line. This is the purpose of the while statement. The condition in parentheses is tested. If it is true, for is less than or equal to upper, the body of the loop, all of the statements enclosed by the braces, is executed. Then the condition is retested, and if true, the body is executed again. When the rest becomes false, for exceeds upper. The loop ends, and execution continues at the statement that follows the loop. There are no further statements in this program, so it terminates. The body of a while can be one or more statements enclosed in braces, as in the temperature converter, or a single statement without braces, as in. In either case, the statements controlled by the while are indented by one table stop, so you can see at a glance what statements are inside the loop. The indentation emphasizes the logic structure of the program, although C is quite permissive about statement positioning. Proper indentation and use of white space are critical in making programs easy for people to read. We recommend writing only one statement per line, and usually leaving blanks around operators. The position of phrases is less important. We have chosen one of several popular styles. Pick a style that suits you, then use it consistently. Most of the work gets done in the body of the loop. The Celsius temperature is computed and is assigned to Celsius by the statement. The reason for using 5.5.0/9.0 instead of the simpler looking 5/9 is that in C, as in many other languages, integer division truncates, so any fractional part is discarded. Thus, 5/9 is 0, and of course, so would be all the temperatures. A decimal point in a constant indicates that it is floating point, so 5.0/9.0 is 0.5555 to the end, which is what we want. We also wrote 32.0 instead of 32, even though since 4 is a float, 32 would be automatically converted to a float, to 32.0 before the subtraction. As a matter of style, it's wise to write floating point constants with explicit decimal points even when they have integer values. It emphasizes their floating point nature for human readers and ensures that the compiler will see things your way too. The detailed rules for when integers are converted to floating point are in Chapter 2. For now, notice that the assignment far equal lower and the test while far less than or equal to upper. Both work as expected. The int is converted to float before the operation is done. The example also shows a bit more of how printf works. Printf is actually a general-purpose format conversion function, which we will describe completely in Chapter 7. Its first argument is a string of characters to be printed, with each percent sign indicating where one of the other second, third arguments is to be substituted. With each percent sign indicating where one of the other second, third arguments is to be substituted. And what form it is to be printed in. For instance, in the statement, printf parentheses double quotes percent 4.0f percent, there must be a comma, percent 60.1f backslash m comma Faraday, comma Celsius, semicolon. The conversion specification percent 4.0f says that a floating point number is to be printed in a space at least 4 characters wide, with no digits after the decimal point. Percent 6.1f describes another number to occupy at least 6 spaces with 1 digit after the decimal point, analogous to the uppercase F 6.1 of Fortran, or the uppercase F parentheses 6.1 of PL/I. Parts of its specification may be emptied. Percent 6 lowercase f says that the number is to be at least 6 characters wide. Percent 2f requests two places after the decimal point, but the width is not constrained. And percent f merely says to print the number as floating point. Printf also recognizes %d for decimal integer, %o for octal, %x for hexadecimal, %c for character, %s for character string, and % for % itself. Each % construction in the first argument of printf is paired with its corresponding second, third, etc. argument. They must line up properly by number and type. If you get meaningless answers, by the way, printf is not part of the C language. There's no input or output defined in C itself. There's nothing magic about printf. It is just a useful function which is part of the standard library of routines that are normally accessible to C programs. In order to concentrate on C itself, we won't talk much about iNatural until Chapter 7. In particular, we will differ formatted input until then. If you have to input numbers, read the discussion of the function scanf in Chapter 7, Section 7.7.4. Scanf is much like printf, except that it reads input instead of writing output. Exercise 1-3. Modify the temperature conversion program to print a heading above the table. Exercise 1-4. Write a program to print the corresponding Celsius to Fahrenheit table. Okay, here it is. Let's take a short break and continue. Okay? See you.